Alabama. All right. Good morning, everyone. So I will be moderating the session this morning, and we're going to talk about the emerging technology called machine learning and artificial intelligence, right? And that's what everybody is talking about, and then that's what's going to replace us, right? So let's start with talk by Negro.
Yes.
And on the application of machine learning for scientific data analysis, and this is a 40 minutes talk with 5 minutes questions.
All right. So the title might be a little misleading. I thought that this is going to be the first talk about machine learning, probably of the whole workshop. So I thought about giving some more basic things about machine learning. So the question for you is, how many of you used machine learning in the past? Any kind of machine? Many of you. Many of you followed like a course at university about machine learning? Fewer. Okay. How many of you have done backpropagation by hand? Well, okay, you thought you were in my class. Okay, you're right. So, cool. Today we're gonna touch upon basics of machine learning. How does that actually work? So probably the ones of you that already did backpropagation by scratch probably know all these things, but it's good to bring everybody up to speed so that then we can talk the same language. So let's start with some terminology, okay? So we talk about training / validation, test, data sets. Which is the collection of our data. Training and validation are part of the training process. Test is something you do at the end. I will touch upon this in a second. We can define examples as the single instances of our data. It could be vectors, it could be an image. Those are examples in your data set. Labels, also called targets. This is more restricted to supervised or self-supervised learning, where you have something to try to match. And we can define also, I'm gonna talk about features, also called covariates. Okay, these are the dimensions of your input, initial input, okay? So if you have a vector of dimension D, D are the number of features in your input. So before going deep, we start understanding how things work in a shallow network. Just to visualize a data set, typically machine learning uses tabulated data, or if you don't have tabulated data, you kind of use a trick to bring you back into a tabulated version of your data. So in this example, we have, for example, 6 features. This is one example. In your data set, you have several examples. Okay, so you can picture your data set like a big matrix. And the target that in this case, I just mark as one single value, okay, is the value we want to learn given an input, or something we want to predict given a new input that we haven't used for learning. So let's start with, as I said, a shallow network that can look like this. In this case, we have all the initial dimension features, this, D. connected to one final value, okay? Y. This is a linear example of linear neural network for a regression problem. So we have a function that maps the RD, where D are the dimensional, the number of features in input, to a scalar value. So the goal is to learn a predicted value, scalar value of Y, given examples, pairs of X and the target, okay? So in a linear settings, this end up being our prediction Y hat being a linear combination of your features all right, where these are called weights. So we have our input that is an array or a vector belonging to RD. We have defined a new vector W, which also belongs to RD, so the same dimension as X. And we have B, which is a scalar value. So these are called weights in machine learning. And this is called bias in machine learning. These are parameters of your model. So weights, the bias itself is very useful. You can think about this. Useful for two reasons. One, if you have a zero vector in your input, you can still give a prediction that is non-zero. And also, this allows you, this is a 1D example where you have your data points, and here is X, Y, okay? In this 1D example, we have our data, and if we don't have the bias, our model could only predict lines that are passing on through the origin. With the bias, this allows us to move from this to something that doesn't intercept the zero. So that's why bias is useful in these settings. But so this can be written in a compact version, right? So we have our prediction being our vector operation multiplication plus E. This is for one example, okay? But as we said, typically we have a number of examples that we can see, and then we want to make our prediction on the best values that give us the best prediction of Y. And so typically we have X, a tensor that belongs to n number of examples, the number of features, and our prediction is an array of values. Again, this belongs to the Rn, number of examples. We have one target for each example. So now, to this goal, we need two ingredients. One, we need a way to measure the quality of our prediction. Measure of quality. And two, we need a procedure for updating our parameters. Okay. So Let's start with 1. So we can keep defining our terminology. Typically, 1 means defining a function, a measure that returns a number that you can then observe and say, okay, this is a good number, this is not. What I'm doing is going in the right direction or not. And we call this objective function. Okay, this could be, for example, the distance we have our data point, and this is, for example, our linear model that we find. We can measure the distance of the true value that we want to reconstruct, which is, probably given by the value on, is the truth that we don't really know, but we have the target, okay? And what we predicted this value to be, okay? So this distance could be a normal, Euclidean distance or something of the sort. And we call, for example, we can define this function as Li, where I is each single example. This is a function of, well, your example is a function of your target and is a function of all the weights and bias of the problem. And typically we define this as 1/2 the predicted, this is for the single example, so it's not I minus I squared, okay? You might recognize this, right? This is the chi-square. And indeed, this is exactly what it's used in machine learning, and it's called the typical loss function for regression problems. So this is not exactly a distance. There's not a square root, right? This is because computationally speaking, it's not convenient to compute square root, and because it's a monotonic crescent function of x, minimizing something that is square rooted or not, it's exactly the same thing. So this 1/2 term, it's convenient for reasons that will become obvious. This is one example. So after seeing all the examples, again, well, let's be explicit about the dependencies. We have, dependent on the full tensor in input, the vector of the labels, and then B. After seeing all the example and having computed this loss function for the single example, we want an average of this loss. So 1/n, I1 to n of all these functions, okay? If you want to be explicit again, this means 1/n, the sum over I, 1/2, and then we have this setting. All right, where here I substituted our predicted value with the operation that depends on the weights explicitly and our inputs. Okay, so now the goal, of course, is to find this W star and B star that minimize this distance of this number, all right? So we want to find this so that our min over the full examples. So now this is easy enough that you can do it analytically. Okay. However, this is rarely the case in machine learning. Rarely you can do these things analytically. So what we need is the second ingredient, a procedure to update the weights automatically. And what we use is mini batch, stochastic gradient descent. Okay, let's break it down. Gradient. Gradient of what? We want to measure the gradient of our loss as a function of our parameters that we want to find, which is DL, DW, and DL. Okay. And this is for all the for all our features. Okay. So we want to find the gradient of our function. The gradient tells us what is the maximum, the direction of maximum increase of our function. And now we want to find the descent direction. So we want to go at the opposite direction because we want to go down to our, imagine this as a surface, and we want to slide down to the minimum of this surface. Stochastic, this is something that tells you we are not seeing all the examples at the same time. We are not seeing the full data set that we have. In fact, without the mini batch, stochastic means I see only one example at a time, and every time I see an example, I change my prediction on the weights, and I do that iteratively. This is very slow, as you can imagine. And only gradient descent, seeing all the examples, can be unfeasible when you have millions of examples. So the middle ground is using mini batches. Okay. How does this work? So here is the procedure. One, select a batch size. This is a number. You define what is the number of examples that you want to see at once before making the update of your predicted weights and parameters. A good number, okay, is something between 32 and 256 in powers of 2. Okay. Second step, once you've done that, you loop over epochs. You define a number of epochs. It could be 10, it could be 100. And what do you do within each epoch? You want to see in each epoch all your examples, mini batch by mini batch. So inside each epoch loop, you have another loop over all mini batch. Okay. Until you've seen all the examples that you have. And in each iteration, what you do is grab a mini batch that is, again, a tensor. And then you compute the average loss. So over the mini batch.
is a mini batch about data or is it about parameters?
It's about data, a mini batch of data. Yes. So this is our data tensor. It's just not, this belongs to our batch size times d. Okay, it's our features and the number of batches. And then you compute the average loss on the mini batch this time. So again, the sum of the I that goes from 1 to the batch size of L, depending on your example, the label, and your parameters. And then you have this. This is a procedure that we'll see. It's called forward propagation. So you compute through the model this value, okay? Do all these operations. And then you compute the gradient of this, which is with some redundancy in or misuse of notation. This is something like the derivatives or the partial derivatives of the weights and biases of this loss function. Let's call it L. Okay. And then the last step, this is where the magic happens. You want to update your initial weights with something else. And this something else is the same values as before, minus your gradient. So minus the gradient, you go in the direction of opposite to the maximum increase. So you go in the opposite direction. And you want to go in the direction by a small step. So this parameter here, eta, is called learning rate. And it's one of the main hyperparameters that you have to fine-tune in your machine learning applications. So what you want to do, if you have your loss function that looks like this, we don't know, this is a manifold of multiple dimensions, okay? But if you find yourself in this point, you want the derivative, so the direction of maximum increase, you want to move in the opposite direction by a small step. The small step is key because if you use the small step and you do the Taylor expansion, you can prove that this indeed gives you a lower value of the function. Okay. Now, just a few notes. Both B, the batch size, and the learning rate are what's called hyperparameters. B and eta are called hyperparameters. So there's what this means is that you decide what these are at the beginning, and there is not a good a recipe to a priori decide what these are. There are good practices, like for example, this is a good number depending on the amount of data you have. But here's the key. How do you decide which parameters are best? That's what we like to do, no? So this is where validation training, the validation step on the training comes in. Because you can monitor your progress in your learning by seeing how the performance, so the loss function behaves when an unseen data point is given. Okay. So here's the key point. So this part is about optimization of the problem, okay? And we do this also in normal, in statistics. We want to find the maximum likelihood, right? But learning is slightly different. Okay, the goals are slightly different. This wants to find the perfect parameters that minimize your loss function, your training function. See your data, you wants to find the best fitting function. Learning wants to do something more. It wants to also predict very well things that has never seen before. So you can see how I deleted it, but if you have your data points like this, right? And you have no limit on the number of parameters that you have in your model, you can easily have a function, right, that goes through all of them, also interpreting the noise as an important information. But what you want to learn is generalize enough so that if you give a new data point that is here, it's well, reconstructed. While in this function, for example, if you want to do this and pass through this point, this will not give a good prediction of that data point that is never seen before. Okay, so optimization is slightly different than learning. So the key is you need generalization. Okay, the learning algorithm needs to be able to generalize enough to unseen data. And so there are different possibilities to do this. One thing, where did I put it? All right. So these kind of problems, we are very used to know what that means. This is overfitting. And this is, happens very much in machine learning as well, okay? Especially when you have millions of parameters. So here's where the validation set is very important, because you can look at the loss function as a function of the epochs of your training, okay? And see that the loss function, the much you train, the more the algorithm learns, okay? So the loss goes down. But if you monitor your validation loss, meaning that at each step, you pick some data that you set aside that are not used in the update of the weights step. You evaluate the model after the updating. You don't change the weights, and see how the loss function looks like for those data points. And at the beginning, it looks okay. But at some point, you may find something weird that happens in your validation loss. Your model becomes too expressive and tries to fit the training samples so well that now when I give a new data point, it's not represented well by the model. This is called generalization gap. And nowadays, deep learning algorithms are anyway perform very well in terms of training loss, or you can quite distinguish them, but all it comes down to the generalization gap minimization. You want to minimize this generalization gap. Okay, so how to do this? There are different methods in deep learning. I can name some. Noise introduction. You can insert by hand some noise intentionally into your data. That creates some, in machine learning, it generates, helps closing this gap, okay? So you increase the noise of your data where to the level that the number of parameters in your machine learning algorithms cannot really fully reproduce them. So it tries to learn the full pattern of it. This is one of the first generalization that were introduced, methods that were introduced in machine learning. Regularization. Okay. Regularization is something that is not only machine learning, it appears in statistics as well. We are gonna see in a second a specific case of weight decay. Another way, more deep learning related for regularization, it's called dropout. And we don't have the time to go through all of this, but if you have questions for me, please find me. Another nice regularization, generalization terms that actually wasn't invented for these purposes, but helps generalization is a batch normalization. And one other thing that it's worth mentioning, I'll put it up here, it's data augmentation. Okay, if you have problems overfitting, if you can have more data in your input, that's the first thing you should do. Okay, data are the main point of machine learning. Without data, you can't really do much. Oh, can do really better than standard techniques. Okay, so let's take a look about this weight decay, because it's also useful in statistics. So given the workshop, I thought this was a good thing. And also we're using this to do backpropagation. So let's understand what a weight decay is. Okay, so weight decay. And now I'll switch to purple because I like it. Okay, this is a fancy machine learning rate to say nothing else than L2 regularization. What is L2 regularization? So intuitively, if you have a function of x, okay, the simplest possible function that you can have is the zeros vector, okay? So building on this intuition, you would like to measure the distance between your function, that is the function of your weights, the multivariate surface, and you want to measure the distance from zero, okay? And you want to somehow put a constraint on this surface to be as close as possible to zero, to the origin. At the same time, you're still asking for the learning to happen. So you're still asking that the loss function is minimized. So you want to fit the data, but you don't want your model to be too liquid around the data points. You want to add a constraint, some sense, to make this surface stiff, okay, not moving too much around the points. So, and you can picture this. Imagine you have 10 features. Each in the linear setting, we have a weight for each feature in a linear in the linear setting. So we can have weight 1, weight 2, 3, up to weight 10. Okay, and here we want to put the value of the weight, okay, the how big this vector or this number is in the vector. And so you can have some weights that are higher than others. And this is because that feature is more important to predicting the value, all right? So ideally, right, when you want to do typical optimization, you want to find the optimal function that has the right number of degree of freedom to represent well your data, but not overfit them. Okay. In this setting, we have 10 weights. Some are small, but are not zero, okay? And this is, let's say, we did the training, and this is the optimal ways that we find to minimize our loss function. But now the question is, do we really need like this degree of freedom? Okay, this is not enough. Is that the feature very important to give us a good enough prediction of our label? Okay, so what you want to do is measure the full the full norm of the vector W, okay? L2 norm, okay? And this value imaging is here, okay? You want to push this value down as much as possible, still be able to predict a good number for your problem, okay? This is what weight decay does. And it's called weight decay because if you try to push this down, imagine that this goes here, this is here, still important, this gets to zero. This gets here, things like that, okay? Effectively, what we are doing is reducing the number of degree of freedom because putting a weight to zero means that you're not using it anymore. Yeah, no way. But I'm not that far. I'm not that far. Maybe five minutes. Okay. So how can we do this? This is very simple. We redefine our objective function as J. Okay. Again, is a function of our parameters. We have our loss functions as before. This is to minimize our training loss on the examples that we see. And we want to add a constraint that is the L2 norm of our vector of weights. We are asking that the magnitude of weights is small as possible to still give us a good prediction, okay? And this is the idea behind it. This is the loss, and this is our regularization. You can think about this as a physics problem. This is our Lagrangian. This is our gravity, for example, and this is our constraint. So imagine you have your mass m subjected to the gravity, and this ball needs to slide down like a surface that it, so this is your constraint, an extra force that you are injecting. So you solve this as in fact, a saddle point optimization. You want to minimize this, but at the same time, you want to maximize this. And that point, the optimal point, okay? So this reduces to a physics problem. Okay, that's it. So now, in the final 5 minutes that I have, right? We're going deep. So the simpler deep learning setting is called the multi-layer perceptron or fully connected two-layer neural network. So imagine all this connected to all the neurons to the next step, okay? So to make me draw everything. And this also here. Okay, so here we have our input belonging to R and D, like before. We have a new layer that we call hidden, that is taking the input. Let me not put the equal, well, this is okay, we can define it like this. And plus B, then now it's also a vector, okay? And our output that takes this layer input gets another set of weights, so we call this one and this two, and this one, this two. Okay, but if you look closely, If you substitute this h to here, right, this part here, and you do some math, we didn't really change anything than before. It's still a linear neural network. Can you see this? So how can you build a deep learning algorithm? The key is that your H is not only defined like this before passing to the output layer, we do some magic. We apply an activation function. This activation function is the key of deep learning that makes it non-linear. This is called activation function. One very common one is called, that is used right now, ReLU, rectified linear unit, which is simply, we call it phi, or phi of x is defined as the max between 0 and x. So imagine you have to draw this. It's basically 0, that means negative, and it basically gets you back the same value for positive values. Okay, this acts like a fire not fire setting, and like this is what happens in our brain. So this actually inherited from neuroscience. Okay. Can I take 5 more?
No.
Okay, and we don't do backpropagation. You want to do your fine?
Yeah, 2 minutes. We have 2 minutes for questions, actually.
Okay, so no questions. Okay, no, but this is the very last part.
It is very clear, so nobody has any questions.
Yes. Of course. Yeah. Okay.
The user account, yeah.
Okay. Forward propagation. We start from our input, and we compute Z. Let's forget about the biases for now, just for the simplicity of the calculations. Okay, so this is the same as bias. And then we apply our activation function. So we define H as activation function of C. And then we have our output layer, which is W2 of H. Again, we forget about the bias. And now we want to define our objective function that we had defined before as the sum of our loss function plus a regularization term, which is, our L, which is a function of the output and our labels. Output contains both our parameters, okay, in it. That's how we calculated it. And S is our regularization term that we defined before. So the L2 norm of the weights 1 and the weights 2. All right. Okay. So now all we need to do is backpropagation. So the goal, if you remember, we want to update our V1 and W1 and W2 with W1, W2 minus eta, the gradient of our W1 and W2 of our objective function. Okay, so we need this. So we want both this and we want Bj, the W2, all right? So I'm not doing the whole calculations, unfortunately, I don't have time, but here's the key. J is a function of L and S, right? Where L is a function of the output layer, which is a function of W1 and W2, okay? S is a function of W1 and W2. So you can see the game, right? You use the chain rule of derivation to compute this, okay? And basically you get something that looks like this. DL and DO. This is not, can't be explicitly computed because it depends on the function L that you use. And then H plus lambda W1, W2. Sorry, this was W2. Okay, this makes more sense. It's easier, it's the outer layer, so we only have one dependence on W2. Here is the more difficult part. Okay. To compute W1, okay, we also have to go through our activation. So remember that J is a function of L, which is a function of O, which is a function of H, which is a function of C, which is a function of W1. Okay. So, and then you also have S, W1. Okay. So this can be also all done. You can do it manually. But the key is that here we had the simplest version of our neural network, okay? This is rarely the case that you have in machine learning. So there are automatic ways to do this, and you never see this when you run your algorithms. It's all handled, fortunately, by the packages that you use, PyTorch, and other machine learning frameworks, okay? So it's good for once to see it, how that's done. But this is how machine learning works. And that's it.
Great.
Good question.
Thank you. And ask questions during the coffee break, please. So let's
There's
move on.
one online.
The next talk is online.
There's a question online. We can't do that during coffee break. that's
Oh,
all.
yeah. That's makes sense. Yeah.
I'll
So-
be very quick. Good morning, Michaela. This is Sukanya. Thanks for a great talk. So, of course, I think that CNNs are very effective at processing large amounts of data, and I've used them in that capacity. But my question is, how can you, if you want to accelerate discovery, by which I mean the discovery of things that are really distinct from our paradigms, how can you deal with outliers effectively? I mean, the things that you've been talking about, weight decay and things like that, they're effectively suppressing the outliers, right? So how do you, in the discovery space, if the goal is discovery, how do you deal with outliers in this context?
So actually, I don't think they're suppressing outliers, but a way to, I understand what you mean. So in the way typically it's done through machine learning to detect outliers, because there are techniques to do that, is to train a machine learning algorithm on things that are common, that are not outliers. This is, for example, used at CERN to, automatically reject some outliers. So you train your algorithm to recognize very well things that are very common. In that point, if you pass something that is not common, the algorithm doesn't perform well. And that's a red flag to tag something that is an outlier. This is also a technique used, for example, to detect gamma ray sources in defense purposes. Imagine you have a cargo that has maybe a gamma ray source that, like plutonium, that decays and gives us some very clear signature of a line in a spectrum. So there is technology that in fact is trained on normal spectra. And then when a cargo that has some plutonium in it that triggers a line, the algorithm doesn't recognize that spectrum and flags it. Actually, I think these are very much effective ways to detect outliers or new physics. Actually, particle physics has been using these techniques for some time now to detect new physics in that way. Of course, you still need a scientist then to interpret what those outliers are. Does that answer your question?
Kind of. I'll be there later in person, so I'll follow up.
Okay, yeah,
Thank you so
sounds
much.
good.
You turn the volume down on my laptop? Right. Please scan the nose and put the whole down.
Yes, I will. Of course, yes. Yeah.
Yeah, our next speaker
Yep.
is Patrick. Gosh.
Yes.
Yeah, and the title, and he's going to tell us about the uncertainty qualifications and the mitigation with machine learning.
Awesome.
And this is a 10-minute talk with 5 minutes question.
I'm gonna need the 5 minutes. All right. Cool. So first of all, thanks a lot for organizing this kind of a workshop. Like systematics is something I think about a lot, and very few people want to hear about it. So I'm very happy to be here talking about all of this. Indeed, this is about someone talk about uncertainties in the context of machine learning, but it's also going to be in the context of particle physics. Yeah, as with any experimental science, the bedrock is uncertainties. So when we put out a result that says the mass of the Higgs is this, the world sees the number in the front, and us experimentalists, we see the number at the back, and a good experimentalist will, I claim, having sleepless nights wondering, did I quantify all the uncertainties correctly? Maybe I've done something clever to restrict my uncertainties. Right, so that's what we expect is happening every night, and then comes the question of machine learning, and it's been an interesting journey over the last 10 to 15 years, where our perception of machine learning has really shifted. So in the beginning, we were quite afraid, and for good reason. Machine learning indeed can capture all these very complex correlations in the data, but it doesn't have the intuition we have. So when we build data analysis algorithms, we intuitively know not to use certain kinds of information that might not be well modeled in our simulations and so on. But the machine learning model will just suck it all up. And so we were very afraid that it would just improve precision in some sense by completely screwing up our analyses, right? Then came what I call the solution era, where we realized that all these intuitive tricks we have that we use to make our data analysis pipelines safe can actually be explicitly incorporated into the machine learning pipelines as well. So these are, for instance, with decorrelation methods, and I'll show you a little bit of that. Then we moved to the opportunity era, where we realized that, wait a minute, machine learning can actually help us propagate uncertainties in a much smarter way and from high dimensions that in a way that we couldn't do before. It would have just taken too much time. So that's when we started to get excited about this. And then comes the revolution, where we realized that machine learning can actually quantify uncertainties in a much more robust way than we could using traditional methods. And that actually allows us to take a leap and start using even more complex statistical methods that we previously didn't dare to use because we wouldn't be able to robustly quantify those uncertainties and calibrate those confidence intervals. And I would say we are about to enter this regime, depending on which corner of the particle physics community you are in. You might be here or somewhere between these two things. Cool. So hopefully in these few minutes that I have, I'll show you a glimpse of each of these things. But to get an idea for what data analysis looks like, in particle physics, we have these gigantic detectors like at CERN. You have about 100 million different sensors. So really the raw image is 100 million dimensional. Nobody's trying to do data analysis on such high dimensions. Instead, we come up with very, very clever algorithms. Hundreds of physicists come together to design a very clever summary of this entire thing into one number. And then, of course, this is just one collision. We have thousands of such collisions. Each of them becomes a number each. And then we don't stop there. We further summarize these numbers into the same page. So that gives you a histogram. The bottom is clipped. right? And this is at the level where we know how to do statistical analysis. Each bin is a counting experiment, so you can use Poisson statistics and so on. So you might have your theory predictions, could be simulations or something else that gives you some kind of a density estimation in the summary observable. And maybe you have a signal model that says that maybe there's some new suffix that would sit right on top of it. And of course, the data is unable, but you can compare the two to try to make sense of what the data is telling us. We often convert any question we're trying to ask in terms of a signal strength measurement. So signal strength will linearly enhance the overall normalization of the signal most of the time. And so you can really compare these two histograms and ask the question, given this data that we have, what is the likelihood that mu is equal to 1? So mu is the signal strength is equal to 1 or 2 or 3, and so on. A lot of our questions can be posed in this way. But then comes the question of systematics. So this summary observable could have been designed by us or by a machine learning model like a classifier. And even traditionally, we've always been worried about systematics. So let's say the ideal case is you want to have perfect, you want to use all the information in your observable. So if you have this kind of signal shape changing, you want to have an infinite number of bins so that you can really capture all these differences. But the problem is often that you have background events, and your simulator might not tell you exactly how to model that over here. And in fact, where you are most sensitive to the signal might be where your different background models give you very different kinds of predictions, right? So you're kind of stuck. One extreme case is you have infinite bins and really try to evolve the data. The other extreme example is you forget about the shape completely. You put everything into a single bin, and then the only information you have is the total number of events that you get. So it's a pure one Poisson number that you can use. But then, of course, yeah. So the question is, am I going to sacrifice this power to completely kill off my background uncertainties, or is there some point in the middle where I can make the best of both? And this is what we've done traditionally. And for those of you who are familiar with the machine learning world, this is a problem we've also dealt with a lot in machine learning. For example, in the ML world, it's called domain adaptation. So if your training data set is only, let's say, handwritten numbers on a black background, but now you want to apply it on new data sets, which might have all kinds of colorful stuff at the back, you want to tell the model to not get distracted by nuisances and instead care only about the salient features that are common between the source and target, right? And you can do this with decorrelation methods. So I'm going to skip the machine learning details, but really tell you what it does. So before decorrelation, you would get that, so Z is my nuisance parameter. So that's if the systematic was different. And I see that the summary observable, so the response function, changes if I change the nuisance parameter. So green, blue, or red. This is not what I want. But when I tell the machine learning model in this loss function to somehow decorrelate its response to the nuisance, it can become completely flat. So the decision functions are now completely flat with respect to the nuisance parameter, and your different colors, the response on the different data sets looks exactly the same. So this is wonderful. You really minimize your nuisance, your uncertainty, but it doesn't come for free. You are sacrificing separation power. So the machine learning model is choosing not to use certain information in the data so that it can minimize these. So this is the analog of the traditional intuition-based decisions of whether you want to use some information or not. So this is what I would call the solution. But this already can go wrong in funny ways that wouldn't happen if you had built the analysis yourself. So there are certain cases where you don't actually model the effect of the systematics very well. In a detector systematic, you know exactly if you miscalibrate something, how it affects all the other measurements. But sometimes you have theory uncertainties. So where you just don't know how to compute quantum theory predictions at infinite order, and it's very complex. So you might have two different groups who've come up with a couple of packages. One package is, let's say, called Pythia, the other is called Herwig, and they make slightly different predictions of what you should see. And we need to assign some kind of an uncertainty to that. It's not easy to do. So we do something ad hoc. We take our data analysis pipeline, run it on these simulations, and see what the difference is. And we somehow use that to quantify an uncertainty. It's not the cleanest uncertainty, but it's something. And we're only measuring this distance, but we're somehow trying to estimate this ball because nature might not even lie on this line, it might lie somewhere else, but this is a 2-point uncertainty, and that's the best we can do. Okay, so now you might be tempted to say, hey, machine learning model, can you please reduce the systematic for me? So design a data analysis method that is as sensitive as it can be while shrinking this distance. So your response to Pitya and Herwig should be the same. And what you're hoping to see is not only does it, you can't see this very well, but there's actually the ball is there. So not only is this line shrinking, but the whole estimated the uncertainty is shrinking. And you hope that that true nature is also still within this uncertainty. But what ends up happening is the opposite. The machine learning model does only what you ask it to do. So you asked it to shrink this distance, and it does that very well, but it does not shrink it doesn't generalize. It doesn't shrink the higher dimensional space. And so your only ability to estimate the uncertainty is now gone because the machine learning has over-optimized on that. And your true uncertainty is totally unquantified and quite large. Right, so this is an intuitive explanation for what happens. Like we have the whole mathematical details in the paper, of course, but I think it's easy to follow what could go wrong. So yeah, these are some things that you need to keep in mind if you want to use machine learning to try to reduce these uncertainties. But you can actually you have a different compared to decorrelation that you might want to consider. Even in particle physics, where things are frequentist, we don't call them priors, but we call them constraints, where we know something about a nuisance parameters, and actually you can try to use that information. In decorrelation, you're really trying to be totally insensitive to these effects, but maybe you don't want to be. Let's say in reality, so let's say in a nominal case, your signal and background are in 2 corners of your phase space, but after you change the nuisance parameter, let's say the calibration or whatever, the centers of the signal and background start to rotate, right? So the optimal decision function here would be a diagonal line. Here, the optimal decision function is rotated. Here, it's something else. But instead of choosing one decision function, I can actually learn it as a function of the nuisance parameter, and then fit the nuisance parameter and the parameter of interest simultaneously to get the likelihood and use that information in an optimal way. Right, so you can do that with what I call uncertainty-aware neural networks, but the network is told how the data changes with your nuisance parameters, and therefore it builds the optimal analysis for every hypothesis nuisance. And then you that allows you to propagate the impact of these nuisance parameters optimally to the final likelihood, and then you can profile it or deal with it as you would in a traditional statistical analysis. And it turns out that works quite nicely. So this is a negative log likelihood curve. It's actually a profile likelihood curve. So the narrower the curve, the more precise your measurement is going to be, and it includes both your statistical and systematic uncertainties. And so we can see how different methods compare. The blue is the baseline where you don't think about systematically, you just train the model on your nominal sample, and then you hope for the best. The red is the decorrelation method. So interestingly, it does even worse than if you didn't think about systematics. That's because the decorrelation method is trying to use none of the information that is tainted by your systematics. And that means it's not using almost any information at all. Right? And instead, if you use that information and propagate the impact of it to the final likelihood, you can actually constrain both the parameter that you care about and the nuisance simultaneously at the end. Okay, so these are all still how machine learning can help with traditional statistical methods in particle physics. Nowadays, we've gone well beyond this. So we generally do unbinned, at least in the latest methods, we do unbinned analyses in high dimensions. And we're starting to think about going beyond the likelihood ratio test itself, where we don't have to So the idea is this, and I think Louis Lyons yesterday hinted at this. Traditionally, we take the high dimensional data and summarize it as we discussed, and then give that summary to the statistical fit. We also have to tell the fit what hypothesis we're testing, and then the fit runs for a while and gives us one time data, right? If you want to get rid of the summary and give the high dimensional data directly to a neural network, we tell the network also what hypothesis it is I want to test, just as before. And then the network directly should give me the likelihood ratio with respect to some reference. Right? And these networks can be trained on simulations and applied on data, hence this term neural simulation-based inference. It's a very hot topic right now across astrophysics, particle physics, and so on. And in particle physics, it turns out that this is essential to model quantum interference effects, which is when you have multiple different Feynman diagrams, they can interfere with one another, and all traditional methods really fail to capture these things in an optimal way. So using the high dimensional information becomes essential. These are techniques we've known about for about 10 years, but have never been applied for real in particle physics because there are obvious questions. Are you really going to trust a neural network to give you a likelihood instead of an analytically known Poisson formula? I mean, I wouldn't trust it 5 years ago. So that was an important question we had to answer: robustness. How are you going to propagate all the systematics? How are you going to do the Neyman construction, which is to make sure your confidence intervals are well calibrated now for a high dimensional analysis? So these are all the questions that we did manage to answer in this monumental paper. It took me 6 years, but it was a much bigger team, and several of us worked for many years to try to answer these questions. So yeah, this was nice, and then we actually applied it to real data. So let me tell you what the core solution was. The main idea says this, right? We use networks to estimate likelihood ratios, but instead of one network, we're going to break up the problem into multiple networks. So each of them is going to solve a smaller subtask, and then we can string them back together using physics-informed formulae. And the physics-informed formulae is essential to make the whole thing robust and possible to validate. Then we have additional neural networks, one per source of systematic uncertainty that adjusts the final likelihood ratio to propagate the impact of their respective nuisances to the final likelihood. And then comes the question of the neural network training. There has to be an uncertainty on that. And so each of these boxes is not one network, but an ensemble of 1,000 networks. That helps us capture this uncertainty very well. In fact, the recent paper that shows some nice theoretical guarantees for how to do ensembling in a way that you can really get 95% coverage with these ensembles. It's quite nice. Of course, yeah, training all of this takes a lot of computing time and so on, but we have that nowadays. I'm going to jump to the results.
Sorry.
Yeah.
You're running out of time completely.
How much time are we?
You have 0. We're negative.
Is this 15 minutes?
It's already 7 minutes.
Really? Okay. Okay, cool. So,
Please
right.
wrap up.
Yeah. So this basically gives you a huge performance boost, so that's very useful. And the Neyman construction I'm talking about, which is very expensive to do traditionally, can again be done with machine learning. And James, who's sitting here, led this paper that shows how to do that. So now I'm going to skip this slide and show this. Yeah, so the point is, you can do about 2 orders of magnitude faster Neyman construction that really lets you use these kind of fancy statistical methods that can bring you about 20% improvement in Higgs measurements. And that brings me to my conclusion. Hopefully I've shown you that machine learning lets you quantify uncertainties now in a better way that lets you do more advanced analysis.
Nice question from the people in the room. Anyone?
I have a question for that comment about
Sure.
not about this, not sorry, I think we can talk about this, but I'd rather have more questions right now. The copy and length are already pretty long. So instead of getting best here and not taking reverse questions, everyone, I'd say find it becomes a little bit into the
Do you want to be the chair?
no.
I have one specific job to do.
then please respect that.
The lunch is 2 hours.
I know, I mean, if that were, then you should provide feedback to the organizers. All right, if not, then, yeah. Let's have, the next speaker. Yeah, and this is going to be 20 minutes up with 5 minutes questions.
Okay.
And we're
Down
going to
is
talk
next.
about, systematics with generative AI.
The microphone is in the laptop, so stay close.
Okay, great. So hi everyone, so my name is Daniel Krishna. I'm a research scientist at MIT and also concurrently an Astro AI fellow at the CFA. So I'll talk today about how we might be able to use generative AI to model systematics, and I'll give a couple of approaches. And for the sake of this talk, okay. For the sake of this talk, I'm going to break down systematics into really broad areas, right? So we've got known systematics, but we know how to do the corrections. In those cases, we don't need AI, right? But in the cases where we know some effect in our data, and we know what causes it, but we don't have a good model to learn how to correct for it, I think data-driven models offer a really nice alternative. And so I'm going to talk about an approach for the first half of this talk on how we can use generative AI and specifically diffusion models to learn systematics from the data. And then we've got the case of unknown systematics, right? Systematics we don't know that caused by our instrument. And Jeroen Ordnat gave a nice demonstration for one way to do this yesterday, and I'm going to pick up from where he left off over the second half of this talk. So, okay. All right, so let's talk about where we have a known systematic, and we want to kind of find a way to learn that from the data. And a really nice example of this is from the TESS mission. So TESS is a NASA mission. It traditionally looks for exoplanets, but it also finds variable stars, supernova, microplanets, and a whole range of other phenomena at very short timescales, the time series data set. But one of the most significant issues, and if anyone's ever used TESS data, it is trouble with scattered light, okay? And the issue is that whenever the Earth or the Moon, here's a nice little animation showing you the Earth and the Moon, the Earth and the blue, the Earth and the gray, whenever they come overhead, the 4 cameras, so here are the 4 cameras, 1, 2, 3, 4, and you can see the 4 cameras on the telescope here. Whenever the Earth come overhead, the light reflects off them, bounces into the baffles, into the sunshades, bounces into the camera and into the CCDs, and you get these really, really annoying systematic effects, these bubbles, these shapes here, that distort the stars and the signals that we care about behind them. And the scattered light, what I'm calling scattered light or stray light, is dependent on the position of the Earth or the Moon and the properties of our lens. So what do we do, and what does it look like at the light curve level, right? So when we construct our light curves from the stars in our images, we can get data that looks like this, right? And the reason you get this double peak is just because TESS orbits the Earth twice per month, right? And stares at a patch of the sky for a month at a time. But if you look at this, what you might not be able to see with the naked eye is that there is an exoplanet signature, right? And if we were to be able to correct it, you can see in this blue line that there's a transiting planet here, a planet falling, transiting in front of its star and causing a slight dip, right? So to show you that this is the scattered light is significant systematic, that it floods our data, right? And the way that people normally deal with this is they either throw away the image that causes that scattered light, they do some median filter over the light curve, or they look at their PSF and they'll sum up the background PSF flux and they'll subtract that away, right? And that's a reasonable program, it's not bad, but it's a proxy for what's actually going on. And so the question is, can we learn this scattered light directly from our data, right? So can we build a data-driven model for these 4 frame images, right? So here are the 4 cameras again. Each of those cameras have 4 CCDs, right? Now, in principle, right, if we fully understood the properties of our lens hood, right, the CCDs and positions of the Earth and the Moon, then we could do ray tracing, right? We could just do this analytically, right? We just do ray tracing, following the parts of the light from the Earth and the Moon, bouncing into the cameras and seeing exactly how they cause these bubbles, these shapes. But we don't understand our lens hood well enough. We don't understand our CCDs. And in fact, we tried to do this and we can't even get the CAD model because it's under control, government control. So even if we wanted to, we couldn't, right? And so the question is, can we learn from the data? And I think we can, because we have thousands and thousands of images that look just like these, right? With the Earth and the Moon at different configurations, all causing these scattered light shapes. So we have this, when all this information about the length of the CCDs are embedded in our data. Okay, so let's try and learn a data-driven model that predicts these shapes conditioned on the positions of the Earth. Okay, so what I'm going to do, and what I'm proposing that we do, is we use diffusion models. I like diffusion models a lot, and if you've never heard of them, you've definitely seen them, right? All of the fake images you've seen these days on by Dolly or ChatGPT all use diffusion, right? And the way it kind of briefly works, and I'll talk about the next slide, is it starts from noise and it tries to predict something that goes from a Gaussian to predict a very obscure probability distribution like the painting you see here. And what I'm going to do is, instead of using it to predict beautiful shapes in paintings, I'm going to predict our boring and annoying systematics. Okay. So this is a project led by one of my great undergraduate students, Drew Tufto, and he's an MIT senior, and previously was by Joey Lupo, who's was an MIT student, but now is at UT Austin as a PhD student. So how does a diffusion model work? Just briefly, and so this is specific, one of the most popular types of diffusion models, at least one first. Well, it's called a DDPM, a denoising diffusion model. And what you do is you start off with an image, right, that you have, right, and you do some forward process where you additively add noise. Okay, and this is a forward process. It's fixed. Is a Markov chain. Basically, you just gradually add Gaussian noise to your images over several diffusion time steps. And I set it to 600 diffusion time steps, but you can do whatever and add in complexity, right? No neural network involved. Just keep adding noise in a Markov chain, right, until you get to something that looks more like a Gauss, right? Gaussians are easy to sample from, and so we're happy about it. Then the process that we want to do is we want to learn that reverse process, right? We want to learn and to predict the joint distribution given a previous noisy image. Can we predict a slightly less noisy image, right? And that process is an easier thing to learn rather than going straight from our Gaussian internal. So learning these small diffusion time steps with a function like this, where we condition on the previous diffusion time step to predict the next one, is an easier process. And the way we can do this is we can use a neural network to do this, right? And so we're going to use a UNet architecture. And UNet architecture is just basically a series of convolutional neural networks, right, that go from one point of one image with several downsampling steps until we get to it. And so we're just going to go from our noisy image to our slightly less noisy image, okay, iteratively over and over. And learning this function is learnable with a significant number of UNets at every time step. Okay, great. So that's what we're going to do. And so in our case, we're using a diffusion model in the same way. And we start off with our scattered light, right? We add additive noise all the way through until we get to something that looks relatively noisy and Gaussian. And then we learn this reverse process with a UNet and diffusion function, right? And that's our method. So can we do this? Okay. Great. And so to do this, I'm first going to do some pre-processing, because what I want to learn is the scattered light. So what I first want to do is I want to say, can I isolate my scattered light? And so I'm going to do something relatively, trying to go from our original image that has both stars and scattered light, and just get our scattered light, right? And just isolate that. So I've got a series of pre-processing steps. And one of the key things here is that I can't deal with the large 4096 by 4096 pixel images that I get, right? And so I'm going to downsample it to 128 by 128, more manageable for my GPUs. Okay. And so I do this median filter downsampling. What that nicely does is it gets rid of most of the stars. And what I then do is I subtract out a background image. And so what is a background image for me? That is an image where I know the Earth and the Moon are below the sunshade, right? And so I know that there is no scattered light in that image, right? And so this is just where there are only stars, right? And, you can't see the stars because the meaning of downsampling, but here we should only be like with stars over here we can see the Milky Way, right? And I subtract that away, hopefully being isolating just the scattered light. And then I do I scale it down to a more reasonable range, and that's my pre-process. Okay. And my goal is to take that pre-processed image, predict the same image, right? Use a UNet architecture to go from this noise to predict that same image, right? But the key thing I want to do is I want to be able to condition on the information I know, right? I know the positions of the Earth and the Moon. So let's condition on it. Okay, and so what exactly, what do I mean when I say positions of the Earth and the Moon? I really just mean the positions in polar coordinates of the Earth and the Moon relative to the sunshade and camera, right? So here's my elevation and azimuth relative to the Earth and the Moon, relative to the camera and the sunshade. Some degenerate information here, I don't need it all, but I'm passing it anyway, okay? And instead of just giving it the distance, I'm going to make it easier for the model, right? I know that the distance, the brightness of our Earth and the Moon scales with 1/d squared. So I'm going to just give it 1/d squared directly, right? And I also know that the angular size of the Earth and the Moon scales with 1/d. And so I'm going to give it 1/d, right? And so this is my conditioning vector. My goal is to condition on this and predict this. So I'm going to go from this nice theta, right? My angles here, condition on this, and I want to predict this, and condition on the original image. But the really neat thing that I can do is that inference time, once this model is trained, I can use these positions directly, right? Sample from my latent space. Here's my latent space. I can sample from this latent space, condition on these parameters, and get an estimation of scattered light without ever seeing the original image. So this is a nice little thing that I get out here. It means I can predict the shape of this scattered light at any time in the future if I know where the Earth and the Moon are. And actually, we're going to use this in a couple of months because we're going to point test at 3I Atlas, the new interstellar object, and we want to make sure that that object doesn't appear in the scattered light doesn't interfere with that object, right? And so this is a really nice use case where I can say, this is where scattered light is in my image. So let's put 3I Atlas over here, away from. Great. So we can do this. We can now predict it without ever seeing an image. And what we can nicely do is we do our pre-processing, we can make predictions. And because this is a diffusion model, it's probabilistic, which means I get uncertainties for free, right? I get a mean prediction and I can get a standard deviation of those outputs as well, which is nice. And the way I can do that is I can sample. Every time I sample from my diffusion model, I get a slightly different result. So if I take 100 samples, I can get my mean and standard deviation. Great. And so ultimately, the goal here is to go from this original image and to predict an image without the scattered light. And so I can subtract out my mean prediction, and you can see that you're mostly left with a scattered light free image. Okay, now if anyone was paying attention, there was a fundamental flaw, right? And maybe some of you pointed it out. And that is that this pre-processing is isolating my scattered light, right? And so why do I need a diffusion model at all? Okay, because I've already isolated. But the thing is, this is not a perfect isolation, right? The subtraction here, the stars are doing funny things, right? They're all doing their variable things. And so this subtraction isn't actually perfect. And so it's not actually a good thing. And so although, here's my original image, although my samples look great visually, when I go to the light curve level, you can see tiny little dots here appearing with the residuals of my stars, right? So I haven't learned it perfectly. And so Drew is now extending this approach. This is all very new work. It's extending this approach where we want to learn, again, we want to learn this scattered light, right? Why? Conditioned on the original image, which has both stars and scattered light. And ultimately what we want to learn is is this difference, right? We want to learn the scattered light. And so we can now take this image, what we want to get is we want to get the scattered light condition on X and condition on my conditional variables, which are my theta, my positions of the Earth. And the way I can do this is I can use what I've just talked about for the last 5 minutes or so as my prior. That's going to be my prior distribution, right, of the scattered light. I've already done this, which is great. And then I want to learn a model of my stars, right, X minus Y, which I have because I've got a bunch of background images, right? And I'm going to subtract that away. And hopefully then I can learn this model directly. And it's this now acts as my prior, and I can learn something more. So haven't done it yet, but I think this is a really nice approach to deal with with problems like this. And while I've shown images here, I think you can do this for any set of data where you have some known causal factors of a scattered light, or you can condition on of the systematic. Okay. Now, in the remaining how much time do I have left? You have 8. Okay, that's okay. What about the unknown systematic arrangement? So I'm going to take a pause from what I just talked about. Okay, so if you've got questions, please leave them for the end. I now want to talk about what about the cases where I don't know what my systematics are. Okay, where here I've pointed out really obviously I've got scattered light. Okay, I know what causes it. Let's model it. Okay, But in the cases where I don't know, my instrument is doing funny things, and we know this, right? In the last talk, we heard about domain adaptation. We know that there's an effect between two different data sets, but maybe we don't know how to model. Like we don't exactly know what are the causes of these different effects. And so yesterday, Jeroen showed this plot, this slide here, and it relies on this assumption that our data is a combination of systematics and a target, right? So how we're measuring our data and what we're measuring. And what we want to get is this, but we're plagued with these systematics. And so the question is, if we believe this, and we have this causal separation in our data, then maybe we can model these things independently, separately. And so, these combined signals are sort of great. And so he showed yesterday that if we rely on the facts that astronomy and a lot of sciences often is we have these really nice properties where we observe the same object over and over again, but in multiple different views, in multiple different instruments. And here, for example, the same star, right, observed in 3 different instrument configurations, right? This is the same star. Now, obviously, you've got phase shifts, but this is one star observed in test sector 14. Here's observed at a different time. Here's it observed in Kepler. Right? Same star, doing slightly different things, but the underlying property, the underlying physics is very similar. Okay. And you can see the noise properties different. So let's try and use this, right? The fact that we have this information where we have the same objects, and maybe we can learn what is common, what is the underlying survey agnostic view of this star, right? And what is the instrument that effects on each, the individual instrument effects. And so key to this, and I think this is the key to this entire Jeroen's talk and the second half of this talk, is creating these triplets, right? These observational triplets, right? Where you have some original star, right? And you have the same star observed by a different instrument configuration, right? And then you have a different star observed by the same instrument configuration. If you construct these, maybe in this space we can learn about the instrument, and combining these two, we can learn about the physics. And so yesterday, Jeroen showed that we can do this with contrastive learning, where you can use, here's a really great paper by Jeffrey Hinton's team, called SimClare, highly recommended if you're interested in contrastive learning. It kind of set the way for multimodal models that we see today, right? Language text models, sorry, language image models, all came initially from this paper, right? That you see from like ChatGPT, et cetera. Where here in the physics space, we just apply contrastive learning. What that means is I take each of these stars, two versions of these stars, two augmentations, I guess you can consider it. You run an encoder. That encoder can be anything, like a simple MLP, like we saw in Michelle's talk this morning, or CNN, whatever you want, right? And then you just apply contrastive loss. What is contrastive loss? It's just a cosine similarity. What is that? It's basically just a dot product, right, divided by the magnitudes. Very simple. Right? You apply that on your latent vectors. And you push these together in latent space and push away everything else. And in this space, we're pushing together the instruments. This is a really nice approach. Jeroen showed this yesterday. And here you can see that, we can now isolate 2 different spaces, physics space and instrument space. All right. And we've got this out now as a paper, so please feel free to reach out to us if you have any questions about it. Now, I want to talk about, one of the issues here. Right, one of the issues that we saw was that there was leakage in our space, if anyone was remembering, right? If we can now have 2 different latent spaces, right? A physics space and instrument space, color-coded by different properties. Here we color-code by sector. The instrument space learns the sector information, the physics space does not. Whereas the physics space beautifully learns about some physical property, but the instrument space has some leakage, right? You can see this leakage of information, okay? And that was a problem, right? Our contrastive learning method somehow was able to leak information into the instrument model. The instrument did learn something. Ideally, my instrument learns nothing about the physics, but it did, right? So let me offer an alternative in my remaining 4 or 5 minutes. How have I got? All right, so 3 minutes. Great. So let's replace the contrastive approach with a generative approach. All right. So this is new work. And so instead of showing stars, I'm going to show MNIST. This is fashion MNIST data. And so here my star is going to be the type of clothing, and my instrument is going to be a rotation or a scaling of this type of clothing, right? And so here I've got a star observed in a particular orientation, and here is it in a different orientation, a different instrument, and here's the same orientation, right? But a different object, different star, a different piece of clothing. So can we replace it? And instead of this contrastive, forget about my contrastive approach, I'm now going to talk about a generative approach to do this, okay? And so what I want to do is I want to learn this star one, instrument I, instrument B, whatever, right? So this particular object, right? Conditioned on these two, right? Conditioned on my encoded versions of these two. Why Z star? I just mean the latent representation, right? So what does it look like? This is my architecture, and this is led by one of my PhD students at MIT, Pablo. He's done some excellent work on this, and he's continuing to work on this. It's still very new work, and we're trying to apply this to a new data set. But what do we do, right? What we want to do is we want to take a particular object, right? Star one, instrument A, star two, instrument B. Okay. In this place, we're going to pass this through the physics encoder because this is where we want to learn. We want to learn the t-shirt. Okay. And here we want to learn the rotation from this view. And so we're going to call this the instrument encoder. Very similar encoders. The encoders, again, can be very simple, MLPs, CNNs, whatever you want, right? And then in our decoder, we're going to take these two, right? And we're going to force the model to predict star one, instrument B, right? That means we want to take the same object, so learn the physics from this space, the type of object, right? And learn the orientation or the instrument from this space. Okay, so predict this. So take the t-shirt, it's rotated, right? It's never seen this at test time, but we want to learn this. And what we're going to use is we're going to use a flow matching decoder, right? So what is a flow match? Flow matching. So what is flow matching? Flow matching is the same idea as diffusion. It's a little bit faster and better. So instead of now doing a bunch of diffusion time steps, we learn with the actual full image. Now we're going to learn a velocity field that connects, that finds the fastest path going from here to here. And we're learning this function. Sorry, we're going to learn this model, right? That's what the conditional flow matching is doing. Really nice thing is we get probabilities for free, right? This is probabilistic. So what do I get? Okay, so what do I? And the nice thing here is the leakage is very difficult, right? It's very unlikely that we're going to get leakage of information because there's two separate avenues, right? This view has never seen this one. All right. So at test time, what do we get? We can see that we get these beautiful predictions. Given this orientation, given this t-shirt, I can predict this like this. And so here you can see a bunch of examples. It works quite nicely and on MNIST data, and we are happy, right? So I can see you standing up. I'm not going to take too much more of my time, but let me just quickly talk about what it is that we have done, right? So we can condition on n samples, right? The advantages of just generative approach is that instead of just conditioning on Z star, just conditioning on star and instrument, we can condition on all the stars that have been observed by a particular instrument, or all the instruments that saw that particular star, right? Contrastive learning gets to do pairwise. Here we can do n instruments. The other really neat thing we can do is we can enable cross-survey generation, right? I can ask the question, what would this star look like if it was observed by a different instrument? Right? It probably improves physics instrument separation. We'll see about that soon. And it can deal with the problem of contrastive learning, where if you have instruments, two different instruments with two different resolutions, and what is contrastive learning doing? It's finding mutual information. If you find the mutual information between a high resolution instrument and a low resolution instrument, mutual information is the low resolution instrument, right? So contrastive learning might fail you. And so this generative approach can deal with this better. So let me finish up because actually that's all I really wanted to say. It works, right? Here you can see there's less leakage. Okay, so in conclusion, right, if we know the cause of our systematics, but we do not have good models, the approach I showed at the start offers a really nice alternative, right? Conditioning diffusion models, right? If you don't know the systematics and you don't know the cause, then the second approach I showed you, right, is using some sort of self-supervised learning to learn a latent representation offers a really nice alternative. So I'm going to finish up. And we're now interested in applying to new data sets. So if you've got something, you see this is a problem, please feel free to reach out. Thanks, guys.
Thank you, Danny. We do have 3 minutes for questions. Do we have any questions from online? Please go ahead. Yep. Okay. Yeah. Perfect. Yeah.
Thanks very much. So I was wondering, after you subtract out like, how do you have space conserve?
So you're talking about the first model?
Yeah.
Yeah. So after you subtract the scattered light, how do you estimate the uncertainties?
Yeah.
Right. So when we sample our scattered light, what we get is every time we sample, we get slightly different result, right? And it's a probabilistic. And so we're actually sampling from our posterior, right? And so that means the entire image we can sample from posterior. We sample 100 times, I can get 100 different posteriors, and so I can take the mean and standard deviation of those to get a reasonable estimate of my. It's about 5% on our data set, but I think we can do better. We're still on the way.
Could you go back to the slide where there was the matrix or the scatter line?
Sorry, which one did you mean?
Yes, this slide 15.
Slide 50. This one. Okay.
So there is no, if we take out the position, there is no time dependent term. Right? So, for example, during solar flare, something like that, which could, change the brightness. Is there any way? Do you know how much that change would be? Is there any way to account for that?
Yeah, it's a good question. Yeah, there is no time dependence. And in fact, I think, I've been thinking about this, maybe we should, because, the scatter light at one point is very similar to scatter light at another point, but actually the position of the Earth and Moon are also very similar. So maybe it learns that. But if there's something else that's affecting it, for example, some cosmic rays or Venus is close by, like a few pixels, no, this model won't deal with it because it's only conditioned on these things. And so in those cases, yeah, this is for the cases where we have a good causal factor. And so, if we believe there's other factors here, maybe we can include them.
Directly, which could be extended to that.
Yeah, I can't think of anything on the top of my head, but let me give it some thought. Let's chat. Yeah.
I was wondering, because it will be a condition like the condition is on so young. So you said, I was wondering if you might not like this feature in the case of when you're in the avoidance angle approach, do you actually, does it actually predict is that all the time, or does it actually show some on those times that it's like those kind of things?
Right. So does it actually predict satellite? Did I miss it? Oh. No, it predicts dark images. It actually light in it. Yeah. And we do actually give it some examples of images where it doesn't. There is no scattered light, and so whenever we give it angles where the Earth and the Moon are below the sunshade, and we show it an image where there is no scattered light, and so it learns that relationship. Yeah. Right. Right. Yeah. So people, it's perfect. It doesn't work, right? Like it removes the broad shape, and actually you do get, when you do this, you do get rid of the large shape, and you do end up with something that looks pretty good visually. But then you go to the star level, and there are residuals left, right? It still has because the stars themselves have their own variants, you actually you are left with some residuals. And so you can imagine just, doing a low pass filter, right? Which is basically what my median filtering is doing, right? That's basically a low pass filter, right? And visually it looks great, but actually on the star level, it's not. Yeah. No. D3PO, tell me about it. Okay.
Great. Let's thank all the speakers this morning, and let's take a 10 minutes coffee break. Yeah. Everyone. We're starting the second session in the morning, and our first speaker is Virtual. our first speaker is virtual, and then Daniel Whitesung is joining us from University of California, Irvine. And he's going to talk about fast estimation of neutron star interiors and uncertainties. Go ahead, please.
Wonderful. Thank you very much for the invitation. I'm very sorry I couldn't join you there this weekend. I couldn't miss up the chance to have a rainy weekend in Southern California. Y'all know how rare that is. But today I'm going to talk to you about a place even more extreme than Southern California, which is the interior of neutron stars, how we estimate their equation of state rapidly and efficiently with full uncertainty propagation. So we're all really interested in questions of statistics and machine learning and pipelines and stuff like that. But of course, we're doing it because we're interested in the physics. So what is the physics question that we're asking here? Essentially, it's what's going on inside these incredible, dense, bizarre objects called neutron stars. Neutron stars are an incredible laboratory for understanding physics at real extremes. These things are super small and super dense. They're called neutron stars, and we think that the outer layers of them are mostly neutrons, but in the core of them, we have forces that are so intense that quantum chromodynamics and gravity mix together in a way that we cannot completely understand or calculate. There's some form of unknown matter at their core, which could be, quark gluon plasmas. It could be Bose-Einstein condensates. There's all sorts of theoretical ideas about what's going on at the heart of neutron stars. And while we cannot ever probe what's inside a black hole, we may be able to learn what's inside a neutron star and therefore get hints towards understanding the universe in situations that otherwise are totally inaccessible to us. My day job is a particle experimentalist on ATLAS at the Large Hadron Collider, so I'm a big fan of high energy collisions. But the LHC probes a very different part of the sort of temperature versus density plane that we're interested in. And it's hard for the LHC to answer questions about things like gravity because the mass of the objects involved in LHC collisions is very, very small. And whereas neutron stars are extraordinarily dense. And so they let us probe matter under conditions that are fascinating and might help us understand QCD and gravity and even give us hints towards quantum gravity. But while neutron stars don't have an event horizon, they're also still fairly inaccessible in that we don't have one here in the lab to poke and to play with. We're limited to what we can learn about the interior of neutron stars from photons which leave their exterior. So for example, the Chandra X-ray telescope observes photons in this energy range here, and those photons are emitted from the surface of the neutron stars. So we have a very indirect bit of data about what's going on inside neutron stars, which leads us to a very classic statistics question, which is, can we infer something about what's going on in the inside of neutron stars, having only observed stuff on the exterior? If of course, the exterior is somehow controlled by what's happening in the interior, if, for example, there's some theoretical model with parameters, then we could infer those parameters from our observations. If we know what that likelihood is, if we know the likelihood of various data given our theory, right? So do we? Well, often in physics, we don't, right? Because we're working at the edge of our understanding. And so what's going on at the heart of the neutron star is complicated, and propagating that information to the surface is complicated. It requires solving these TOV equations, which are highly nonlinear. And then it involves understanding not just the photons that are emitted from the surface, but how those photons are observed by the telescope, because our data, of course, is not perfect. It has to include effects of resolution and telescope response. So we have a good understanding of some of the pieces, but does that mean that we have the complete likelihood, the probability of seeing our data, the spectrum in the telescope, given the parameters of the model inside the neutron star? We don't, unfortunately. We can't write that down. But that doesn't mean that we're stuck, right? We don't have the likelihood, but we do have something else, which is that we have the ability to do a forward simulation of this process. And of course, forward simulations famously effective in predicting what's going to happen, even if you don't have an analytical likelihood, right? Like in the case of hurricane predictions, is that hurricane going to hit Alabama or not, right? Depends on a bunch of simulations that people have run, which gives you a description of what might happen, right? And then, of course, you add the Sharpie effect, which is a well-known systematic uncertainty. So that all sounds great, but we're here today talking about systematic effects and uncertainties, and especially machine learning. So how does machine learning come into this problem? Well, we wouldn't need machine learning if we weren't in this situation. We wouldn't need machine learning if we could express the likelihood of seeing our data. We could just analyze the data, extract the parameters, we'd be done. If we knew how to write down that likelihood, we'd be done, of course. Or because we have a simulation chain that can go forwards from the parameters to the data, we could also just simulate it. And if we could simulate an infinite number of these scenarios and fill the parameter space of observation with hypothetical examples, then we could perfectly describe it. Or if we had an infinitely fast simulation, which is equivalent, then we also could just, use histograms or something, and we wouldn't, and do simple density estimation, and we wouldn't need machine learning. So basically, we have to go to machine learning because we don't have this likelihood and we don't have perfect or infinitely fast simulation. All right, so let's dig into the details of the inference chain. The X-ray spectra are sensitive to what's going on inside the star, but indirectly. Most directly, they're sensitive to the two parameters of the star, mass and radius. So here, for example, are the number of photons per second over the energy range for various values of the mass of a neutron star with the radius held fixed on the left, and various values of the radius for the mass held fixed. And so these are neutron stars order mass of the sun and radius 10 kilometers, right? These are crazy astrophysical objects. But you see that there is a strong connection here. Changing the radius or changing the mass, both of these affect the spectrum you observe. And so you could, in principle, do the reverse because the parameters do control the observations. And then the next step is to deduce what's going on inside the equation of state of the interior of the neutron star from the mass and radius. So what we're looking at here is the mass radius plane, and each line is a model of possible neutron star parameters that depends on a particular model of the interior. So one model, for example, GS1 predicts that neutron stars never get above 1.4 solar masses. That's one particular line. Well, another one, MS2, predicts they get all the way up to 2.5 solar masses. And you see on this curve also some observations. These horizontal bars reflect real observations of neutron stars, which already rule out some of the EOS parameters because they are more massive than predicted by these parameter values. All right, so we have this sort of two-step possibility for the inference. We have X-ray spectra, which depend on the mass and radius of the neutron star. The mass and radius of the neutron star then depend, in turn, on the equation of state of the interior, right? So in principle, we should be able to, deduce from spectral data what's going on, which EOS theory, what the parameters are of the EOS theory. Okay, and so getting into the details here, how do we actually do this? Well, we can think about the problem in forward direction or in the backwards direction. So in the forward direction, where we start from the equation of state, right? And we say, let's choose an equation of state, then we can solve the TOV equation, which is nonlinear but solvable, to predict the neutron star mass and radius. From the neutron star mass and radius, we can then simulate the X-ray photon generation and the telescope response. There's a program called XSpec which does this, and that gives us an expected X-ray spectrum. So we can go from equation of state in 2 steps to the predicted X-ray spectrum, right? Can we do the inverse? Can we do the inference? Well, XSpec is a program which encodes a likelihood of generation of these photons and telescope response. And so that likelihood is inside the code. And so we can use also the code to just invert that and say, if I have observed spectrum, what are the neutron mass and radius values that are consistent with that? So that step is possible. The next step to invert the TOV is very, very hard, essentially impossible. And so we can go from EOS to mass and radius to spectrum. What we want to do is go from spectrum to mass and radius to EOS, right? In addition, we have other parameters. So we have this, and this meeting is focused on systematic uncertainties, and so we have to also acknowledge that there are other things that can influence the observed spectrum. For example, the effective temperature of gas between us and the neutron star, or the distance of the neutron star. And so, and these, as you can see from these plots, have a strong effect on the predicted spectrum we should expect from any individual neutron star. For an individual star, we expect to have some information about these. This is not completely unknown. And so for some cases, we'll have very tight measurements, like we'll know the distance to a neutron star because it's near another object that we can measure the distance to, or we'll have other measurements of the gas, etc. And so we consider three cases in our analysis: true, where we know these things exactly and we've ruled out the nuisance parameters; tight, where we've measured them well; and loose, where we have only very broad information. And if you look at the data from neutron stars, you see that they occupy this mass radius plane, but the shapes are very weird. They have these weird beans and these blobs, and these are due to the nuisance parameters, the fact that they distort these spectra. Okay, so we're not the first group to attack this problem. There's a nice paper by a Japanese group, Fujimoto et al. In 2019, and they worked on this, the hard part of this, which is going from mass and radius to the equation of state. And before they attacked it, the state of the art was to use the mass and radius data to sort of fit a curve, a mass radius curve, and then try to use that to invert the TOV equations. And what they did was they assumed the mass and radius data were all uncorrelated 2D Gaussians. Now, we saw from a couple of slides ago that doesn't accurately describe everything that's happening, and that's going to be a focus of what we're working on to try to make that more realistic. And they essentially just trained regression to go from mass and radius blobs in this mass radius plane to the equation of state. And then they trained this on toy data and then from simulation, and then applied it to real data. All right, so our goal is to use more realistic uncertainties and to propagate the uncertainties all the way to the final result, and to do end-to-end inference, to go all the way from spectrum to equation of state. So one question is, how do we treat our nuisance parameters? And so regression, in this case, only produces a point estimate, no likelihood. So it doesn't allow us to do things like profiling, though we're going to talk about that in the next section. But these networks we use, we just train them as a function of the nuisance parameters. In that sense, they're what we call in particle physics parameterized neural networks, right? Essentially, we're learning a function, but the function is a function of an external parameter as well. And that gives us a handle where we can just turn the knob to vary the output of the network. And so this gives us, we're learning the problem essentially conditioned on the nuisance parameter, which lets us then vary the nuisance parameter to the input. And given our knowledge or our auxiliary measurements of those nuisance parameters, we can then use that to propagate the uncertainty forward. All right, so we generated a bunch of examples. We picked a bunch of spectral parameters from the plane. Here, lambda 1 and lambda 2 are the theoretical parameters that define the equation of state. And then for each of them, we ran the TOV equations and get a curve in the mass radius plane. And then we started by just trying to learn the mapping between spectrum and mass and radius. And so here we just take the input spectrum and feed it into a network along with the nuisance parameters and use that to predict the mass and the radius. So not yet going end to end, just seeing, can we learn it? And so first we try the easy thing, which is no noise, no statistical fluctuations, no nuisance parameters, and can we predict the correct mass and radius? And we get that bang on, that's the red curve, but that's easy. And then we add noise and we see that you see the kind of dispersion that you expect, still again, peaked at the right answer. And when you add the nuisance parameters in the various cases, true, tight, and loose, you see the expected performance, that the true values of the nuisance parameters now with noise get you peaked at the right value, but very tight. And as you add uncertainty in the nuisance parameter values, you get uncertainty in the prediction of mass and radius. So that all looks very nice. And you can also do something cool, which is you can propagate the uncertainty. And so here, what I'm showing you on the left is the predicted mass and radius for one individual spectrum. But the green points show you what happens when you vary the nuisance parameters within the auxiliary measurements. So you have some information about the nuisance parameters, and you essentially sample from those priors and choose different values, and then you propagate it through the network and you see how that affects your mass and radius distribution. And notice these are not nice uncorrelated Gaussians, right? The effect of the nuisance parameters can distort these measurements in very interesting ways. On the right is another individual example. And so the red dot is the mean, and the ellipse is an attempt to fit an uncorrelated 2D Gaussian to it, which you can see certainly does not cover the uncertainties. So this definitely justifies doing something more interesting than summarizing the uncertainty in mass and radius as a simple Gaussian. We want this captures this method where you learn the problem as a function of the nuisance parameters and then vary the nuisance parameters to propagate the uncertainty through it, captures the full variation and the dependence on the nuisance parameters. Okay, so we've gone from spectrum to mass and radius. Now we want to do mass and radius to equation of state. And here we have multiple stars because a single individual neutron star just gives you a point on the mass and radius plane. But in order to determine the equation of state, you need multiple stars in order to determine which function essentially the equation of state maps out on the mass radius plane. So here we take the mass and radius values from 10 different stars, pass those into a network, and learn the theoretical parameters of the equation of state. And again, here, what I'm showing you is for an individual data set, just a sample simulated data set on the left, and then a different data set on the right, so you can get a sense for how each individual data set has its own quirks. And the green points, again, are data propagated through the same data, but with different nuisance parameters propagated through the network. And so by sampling from the nuisance parameters, you can get a sense for the dependence of the prediction on the values of the nuisance parameters given their uncertainties. All right, and so with that setup, having shown that we can learn to go from spectrum to mass and radius, and then from mass and radius to equation of state, we said, let's do the whole thing. Let's just throw all of the data, the input spectra from 10 different stars, and the assumption about the nuisance parameters into the network, and see if we can learn the equation of state. And we can, and it's just chaining two networks together effectively without stopping in the middle to learn mass and radius, which is, useful intermediate, but not completely a sufficient statistic and not the thing we're actually interested in. What we're interested in are these theoretical parameters. And so again, we have the mean prediction, but we also can sample around and see how the prediction depends on the variation of the nuisance parameters. And for different data sets, you get quite different kinds of predictions. Overall, of course, this thing predicts the theoretical parameters without bias. Here we're showing, again, in the three scenarios, true being no nuisance parameters, or the exact value of the nuisance parameters, tight and loose being well-constrained or loosely constrained nuisance parameters. Left column is the first theoretical parameter, right column is the second theoretical parameter, and the three curves show you some comparisons of different methods. So the red is our neural network end-to-end that goes from 10 different spectra, right? So hundreds and hundreds of inputs to these nuisance parameters. That's the end-to-end one. And the green is when, the blue is the network that takes you from mass and radius from the network, and then the rest from XSpec. And the last one is when you use the neural network using XSpec to do the inference in the telescope step. So the green is sort of the best that you can do, and the red is our attempt to learn the green. And note, so here's some numerical comparisons. The interesting thing is the sigma parameter here, which is essentially the width of this distribution, which tells you the amount of information you've extracted. The green is the sort of upper limit of what you can do here, because the data are generated using XSpec, and then XSpec uses the analytical likelihood in that step. And so you can't really do better than that because the data perfectly match that part of the likelihood. But what we have shown is that this allows you to propagate uncertainties all the way through the whole chain, end to end, with those uncertainties. And while these data were generated using XSpec, nobody believes that XSpec perfectly describes all the data that is out there or all the scenarios. And there are other competing models. And so using a neural network allows you to learn something more general without making an explicit assumption of what the likelihood is, or that you're, and to generate data which don't follow one theoretical model of that likelihood. And you could, for example, learn things which interpolate smoothly between various theoretical models. And so we think this gives you a significant useful flexibility. But in the end, this is just making a point estimate, right? Is that really what we want? We did that initially because it was our first approach, but what we really want is the full posterior, right? We want to know what is the probability of various theoretical parameters given the data, not just a single point estimate. Regression is fine for a first step, but we want to see the whole spectrum. And so to do that, we need to know the likelihood, we need the prior, we need the evidence, right? But again, we don't have all of these things. This is a complicated setup here, and we don't have the full likelihood, especially for this piece here that goes from the that connects the mass and radius to the equation of state. And so we'd love to have access to the likelihood because that allows you to do things like combine the results from other sources like gravitational waves or from other telescopes. And it lets you do things like profiling. And so we'd love to have the full likelihood, not just a single point estimate. Right. And so the goal then is to take a network which takes your observation and all of your nuisance parameters and learns the likelihood as a function of that data. Right. And so the way to do this is to learn the probability density in simulations and then apply that per data on the star. And these networks, we hope, will also give us access to the shape, the full contours here, including all of those gradients. And so this network, we use neural simulation-based inference, which is a wonderful technique and allows you to then scale to a variable number of stars because the application here is permutation invariant and is common across the stars. And so there's some links here to the technique we use, neural simulation-based inference. In particle physics, it was pioneered by Oishik, who spoke earlier this morning. And so he did most of this actual work. Let me show you some of the results. The results are really nice because now we can get so we can scan the full space of likelihood, which means we can get meaningful posteriors, right? So here in the mass and radius space, for example, we can get the 68% contours, the 95% contours. We can do the whole thing. We can even look at the correlation between all of these parameters, including the nuisance parameters, right? So here we're seeing the best estimate, which is the point. And in addition, we're seeing contours under various assumptions of the nuisance parameters. So we can really get the whole picture of what the data are saying if we use neural simulation-based inference to infer the full likelihood rather than just the individual point estimate. And a lot of this work was done by Oishik together with his team using powerful computers at NERSC. And you can look at the table, but essentially this is the most precise measurement we have, and it does even better in more realistic scenarios. All right, so our goal was to do realistic propagation of uncertainties using a full pipeline that goes end to end. And so we quantified realistic uncertainties, and we then used likelihood-based methods, neural simulation-based inference, to do simultaneous profiling and to access the full posterior of the neutron star interior. All right, thanks very much.
We have 2 minutes for questions. Do we have any questions first online? Okay, and then from the audience, please, go ahead.
Should I come there?
Please come over here because otherwise cannot hear us.
Thank you for the talk. I was just wondering if these models can be informed using the results from, for example, pulsar timing arrays, because those can constrain the neutron star mass very well. So is there a way to include that also in our data that we looked at here?
Yes, great question. Thank you very much. So in the first method, we can include other information sorry, in the first method, we can't easily include mass information. We can include information about the other nuisance parameters from auxiliary measurements, the distance, the gas columns, this kind of stuff. But the advantage of the second method is that it produces a full likelihood. And so you can combine that with likelihoods from other sources, from pulsar timing arrays, from other instruments, from other models, etc. And so essentially it captures all of the information in a way that's easy to combine with other information. So absolutely. And that's one of the reasons we wanted to move beyond the regression and calculate the full landscape of the likelihood.
Great. Any other questions from the audience? I will ask a question then, Daniel. So I wonder from based on what the toy spectral that you showed, and the spectral depends on both the radius and also the mass and also temperature, how badly correlated they are from a real data inference. So
Yeah,
if we,
cool
yeah.
question. Yeah, the next step for us is to try to actually apply this to real data. And then we need to include things like uncertainties in the telescope response, right? Because here we're assuming the telescope response, and there's of course always uncertainties in those models and inaccuracies. So that hasn't been included at all, but that's something we'd like to look into, to include realistic uncertainties in the response.
Okay, great. Thank you very much.
Thanks, everybody.
Can we get you? Or that the remote system? Like you wanted a clicker, right?
I can do the click.
Okay.
I can do it click. It's okay. What's that? Okay.
All right, great. So our next speaker is going to tell us about data-driven source locator for gamma ray sources with neural network.
All right. Hello, everyone. My name is Mohammad Ali Burman. I'm a second-year PhD student at Louisiana State University, and I'm working with Professor Michela Negro. The main focus of this work is to design a machine learning system that facilitate the localizations of the point sources in gamma ray telescopes. Specifically, the COSY project, which is a new NASA mission. If I would like to give you an overview of the COSY, so COSY is a Compton spectrometer and imager spacecraft that will be launched in 2027, and is a Compton telescope in a range of 0.2 to 5 MeV. And it has some unique capabilities, like a high purity germanium detector, which provide an excellent energy resolution, and everyday all sky survey that make it unique respect to the previous missions of the NASA for probing the gamma ray sky. So it has some previous history, and it is based on a successful balloon flight missions that happened from 2005 to 2016. And the project will start in 2020, and right now is in a building phase. So, but what a motivation to having a new other Compton telescope? So the main reason for that is the MEV gap. So this is the least explored region in electromagnetic spectrum. We know that because due to the low interactions cross-section between photon and matter, and the Compton scattering is the dominant mechanism in this range. And also we want a telescope, not only a telescope, but also we want a good pipeline, good analysis systems also that can help us to explore better the data that we will give from this telescope. So the four motivations of the COSY is, one is the uncover of the origin of the galactic positrons, which one of the unsolved questions in a high energy astrophysics yet. And we know that this energy range is very good for element formation study. And also polarization, which is another tools that COSI will COSI will have and help us to probe extreme environments. And also we can do multi-messenger astronomy with combining, for example, data from COSI and other telescopes or ground-based observatories. So if you look at all of these four main objectives, the importance of the source localization is remarkable for these telescopes or all other gamma ray telescopes, Compton-based telescopes. So, but what will be look like the data of a Compton telescope like COSI? So when we have a gamma ray photons that interact by the detector, after multiple Compton scattering, it will be absorbed as a photoelectric effect. And for every photon event, we will have two angles, which could be in a coordinate system of the spacecraft or in galactic. And we will have a phi angle, which is the Compton scattering angle. And we will have energy. And if we allow, for example, the detector get information for a long time, for example, for T times, as a result, for a point source, that is the main study of this work, we will have a right cone like that, which the head of that is the location of the point source in the galactic or in a spacecraft coordinate. And the form of this right cone, the z-axis will be the phi, will be the Compton scattering angle. And this basically will be the point spread function of our telescope, which the angular resolution will be the thickness of that. So as you will see here, the Compton data space is a multidimensional data space. And if everything be good, everything be okay, we will have a complete cone. But in reality, we will have interstellar medium and any other effects that doesn't allow us to, we will see, for example, a complete cone like this in a Compton data space at a specific energy. So we will have some geometric ambiguity. Also, we know that the arm value are energy dependent. So basically, we have limitation in resolution. So in lower energy, we will have bigger arm value. And also, we should not underestimate the effect of the background. So the background also very dominant at this range. So what we want to do, we want basically to use the information in Compton data space for a point source using machine learning and probing part of this Compton data space and localize the point sources in a galactic plane. So this is the overview objective of the project. Right now, what we are doing, we're working on a toy model, which for us generate a Compton data space, a portion of the Compton data space, and concurrently make for us a gradient map that the brightest pixels are the location of the head of the point sources. And this Compton data space is manipulated. So for example, we have some points that have more brightness, some of them has less brightness, some of them doesn't have the head. So basically, we make some manipulated 3D being CDS. We design a training 3D CNN, and we train that. And we want to test by other data sets to whether we can generate, for example, a 2D gradient map that gives us the brightest points, gives us the head or the location of the point sources in a 2D projection or in a galactic plane. Then after that, what we can do some peak analysis on top of that. And for example, exactly localize the position of the point sources. So for this work, we basically generated 100K of these ROIs with a maximum number of 6 of these ROIs. And we start with the 0.5 MeV energy as an example. So basically, our data is only for one energy, but we can generate for a range of energy. And the number of the events, the average number of the events for this study, we put 6,000. And the standard deviation, so we use a Gaussian distribution to distribute the number of the sources, the number of the accounts for every sources. And also we consider a constant background for this work, which will be improved for the other other steps of this project, but right now this study is for 2000. We also select a bigger ROI, so it's 64 by 64, and we only use portion of the Compton data space, which is from 0 to 20. And as I mentioned to you, we manipulate the head of the cone by, for example, from 2 to 10, which will be randomly selected every time that we generate a new ROI. And then we bin this data set by 16 by 16 by 16. So all of the motivation of this works, we wanted to start with the simplest toy model and check whether we can reach to the goal with less computation hours and less computational hours, and also better, for example, reach to the better resolution by using a small data set and also bigger resolution. So this is one of the examples of the bin CDS that I generated. And you can see here, for example, these are one of them that we manipulated, and this is the complete one. And this is, for example, the galactic coordinate for that. Then we designed two 3D CNN. In the first design, which has about 1 million parameters, we feed the CDS as the input, then we compress in all L, B, and phi angle. To the end, we reach to the one-dimensional array, which we can make a 2D map from that by reshaping. And if you see here, from here to here, we, for example, use a traditional 3D dimensional CNN, and we put, for example, a linear layer at the end, which makes the number of the parameter a big number. But in the second structure, what we did, instead of compressing in all three directions, we only compress the CDS by using the kernels only from the phi direction. So at the end, we will have 64 by 16 by 16 array, which we do averaging on all of these channels, and we generate the 2D map, 2D gradient map that we want. These are some information about of the hyperparameters that we use for our structure. So the important things here is that we use batch size 64 for 20 epoch we train our algorithms, and we do not use the cross validation. And if you see that all of the effort is to keep the size of the data on the disk small. So the input size is about 17 kilobyte, and the output is about 1 kilobyte. And we use a loss function, which is a simple MSE loss function. The interesting thing that we found during this training and testing is that for the version 1, the total training time is about 5,000 seconds. But for the version 2 is about, for example, less than half. And what we get is that the performance on MSE for the second version also has a very, very smaller number of the parameters, is much, much better than the version 1, at least in 2 orders of magnitude. And the performance are same. So if you look at here, this is the 2D projection of the manipulated Compton data space. This is the ground truth gradient map, and this is the prediction of the algorithm that I have. So this is for the version 1. I put two examples here, and also here for the version 2. If you look at if you compare these two, with a simple comparison, we can see that the performance by a smaller, much smaller number of the parameters are same. So if you look at here, for example, this pixel, which should supposed to be this one. So this is the prediction from the CNN version 1. And if you look at here, we will see that the location of the point sources approximately is correct, but the contrast of the gradient map still is lower than the ground truth. So what we did all of the, so we designed to plot two histograms, which this histogram is a residual, basically histogram of the prediction minus the true for every pixels in our testing data set. And we will find that there is a functional systematic, if you call it, in a value of the, in a residual between the prediction and the true value, between both CNN1 and CNN2. And still, we found that both, if you look at these predictions also, residuals, you will see that still we will have somehow the same shape or same performance. Although the number of the parameters in a version 2 is much, much smaller than the version 1. So basically, for the future work, this is work still is at the beginning stage of that. So for the next step, what we want to do, we want to use Megalib, which is a very more realistic simulator for Compton telescopes. And we simulate basically random persistent point sources. And also we can use Megalib to simulate a much, much better realistic background. And we use physics-informed machine learning to apply the physics of the Compton physics also inside of the loss function to see whether we can reduce these systematics in our output and improve both the localization of the point source and also the contrast of the gradient map. Thank you.
Can take up some questions. Again, first, do we have any questions online? No, then it's floor is open for questions. Oh, there's one.
Okay.
Can you go back to slide 8, please?
Okay.
I must have the wrong slide.
This one?
There we go, slide 7.
Okay.
You chose an arm cut of 4.1 degrees. What was your, why did you choose that?
So basically, we have a function that shows us the dependency between the arm value and the energy. So that function comes from the response of the detector respect to the specific energy that we have. So I use that function and select, for example, for the energy that I want to do the simulation, what should be the value of the arm value, the arm value. The arm value. So basically, these arm values comes right now because the people at Berkeley, UC Berkeley, that are the PI of the project also is there. They use the Megalib for the simulation of the detector. They simulated the response function and also simulated the detector by the geometry and all other parameters. And they generate this value for the arm function. So I use that data to select the arm value for my simulation. Basically, if I want to simulate for a range of the energy, then I should pass I basically get the correct version of the arm function respect to the energy to my simulator, so select the correct value. And also here, I didn't apply the Klein-Nishima, also probability distribution, because this is a very simple toy model. But if I use the Megalib, also I can apply the dependency of the scattering angle respect to the energy better. So which is the next step that we want to do.
I have a question.
Mm-hmm.
So COSI is this 511 keV,
yeah,
right? Design, and I heard that it was using the multi-layer coating of the mirrors to actually make the grazing angle to be larger so that it can focus light.
Okay.
And then that multi-layer design is tuned for specifically this to enhance the reflectivity of the 511 keV. So it also serves as a filter. So if in an alternative design, without that focusing telescope that is floating, I don't know, 1 mile away from your detector, and your detector will not have any energy sensitivity. Is that right?
I'm not sure about that.
Okay. So what I mean is that how do
anything.
you actually make sure that the event is actually 511 keV?
Oh, you're talking about the event selection.
Yeah,
So
yeah,
basically,
event selection,
these data. Oh, okay, it's a good question. So Basically, I didn't put here, but I have another slide that I can show you. So basically, the data that we get from the telescope has several levels. So the data that we have is the data that is ready for analysis. So there are some steps before that to remove, for example, some events that are not related, for example, to the true astronomical source. So we have a hierarchy of the data, so that everything will be happens before this layer that we call it L2C, if I do not make mistake. So after that, after this layer, we ensure that a great majority of the events are the correct events that are not related to the, for example, any effects that are related to the detector or something else around it, for example, like photon albedos or something like that
Right.
we will have.
So in your simulation, you're assuming that the telescope does not have a focusing optics.
Mm.
Okay.
You can answer.
Mhm. Yeah, so currently there is no plan for focusing optics.
No, there is no focusing there. There is no.
Okay, got it. Yeah, yeah, right.
There is no focusing. Yes.
So that must be a future mission.
Yes.
Yeah.
You are very welcome.
Yeah. Okay, cool, great.
Okay.
Thank you.
Thank you so much.
All right, I gotta find the next presentation.
We have the speaker. We're not seeing the presentation.
I don't think so.
Do we see the presentation? Okay.
I don't know who this is.
This is a P. Jalan.
She's in Poland. She was marked as attending in person on the spreadsheet.
Uh-huh.
My thoughts would be that in fact, there was, I believe that there might be a mistake.
Okay.
So actually, that would give me an opportunity to pass along a couple of information about tonight and the afternoon session, okay? So tonight is the conference dinner at the Space and Rocket Center, okay? So we will actually have the opportunity for a private visit there as well, okay? So the idea would be to be there at around 5 o'clock, okay? Now, then at 6 o'clock we will have I know there will be I think, what do we call it, a plenary talk, talk about gravitational waves, which I thought that would be nice because it's some anniversary of gravitational waves, right? 10 years, is it? To me, astronomy is still electromagnetic waves, but I guess it's a brand new world. Yes, so that's the reason, and then there will be dinner, okay? And so I was thinking that since the program here is a little unclear, it's my fault. I cut this, and so I want to fix this. So really, we should be there at 5 o'clock. So that means, by the way, that perhaps I suggest that in the afternoon, especially with the longer break that we have now, let's try to start at 1:30, 15 minutes ahead of this schedule that we have here, okay? So that way we kind of have an opportunity to, whatever we want to do between the end of the afternoon session and our dinner. And I just realized that I think that John Morales' talk, instead of being a talk, is a poster that is there. So there will be also one fewer talks there. So today, there are a couple of imprecisions here, and they're both my fault here, okay? But anyways, I would say that, so lunch break now, okay? And then we'll come back at 1:30, please, as we were slightly ahead of schedule, okay? So that I think it should work out, okay? So yeah, let's just do that, okay?